So sorry for that to those who wasn't able to watch this one, since I'm pretty sure that some of your classmates will watch the recorded Zoom meeting. So let's just go back again, okay? Real quick, okay? So in here, uh, here's the slide one, and then the definition of the Kirchhoff's law, okay? Wherein the main definition why we have this law right here is for us to be able to solve a more complex circuit problems, okay? Like, for example, the bridge resistor circuit and then the T networks. Second one is the man who found out or developed this law. So his name is Gustav Kirchhoff. So he's a German physicist. So he was able to develop this one way back 1845. Okay, and then this law right here is divided into two. We have the KCL and then the KVL. KCL is for the Kirchhoff's current law, and then KVL is for voltage law. Okay, and for the KCL, so we just have a simple rule right here. So the total current or charge entering a junction or node is exactly equal to the charge leaving the node, as it has no other place to go except to leave, as no charge is lost within the node. So just like what I mentioned a while ago, so if we have a current of, say, 1 ampere right here, upon passing through a node, it is still 1 amp right here, but this one is not applicable with parallel, since this one up will be divided into two, since this is a parallel. However, if this is a series circuit, so let's make this one a series circuit. Okay, there you go. So we just have a one loop. Okay, so whatever is your current right here, upon passing through this node, it is still 1 amp right here. Okay, because there is no other way that that current will go to. Okay, so that's the rule when it comes to KCL. Okay, and then for this one, here's the equation when it comes to KCL. So we just have a simple rule. If it's entering a node, we have a positive sign. If it's leaving a node, then we have a negative sign. Okay, so that is why if you are going to take a look on this one, so we have, let's say, your 1 amp right here. So that's entering, so that's positive 1 ampere. Okay, and then we have a current that is leaving this one. So this one is now equal to or minus 1, okay, or 1 amp. And then equate that one to 0. So 1 minus 1 is equal to 0. So 0 is equal to 0. Okay, or if you want, you can transpose this one on the other side. So 1 is equal to 1. Okay, so that's basically the rule of the KCL. All right, so more explanations when it comes to the KCL. So here's the initial equation wherein we have a positive sign, but of course you have to negate those leaving currents. And then here's now the simplified version of that one. Okay, so positive, 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 and then two negatives. All right, and then here's the definition of a node. So a node is just basically a function, junction. Okay, so this is a node, 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 and so on and so forth. Okay, and we now have the second law, which is the KVL, or the Kirchhoff's voltage law. So KVL, or Kirchhoff's voltage law, so this is the definition, okay, or the rule itself of this one. So in any closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop, which is also equal to 0. Okay, so meaning, let me just get this one. So if we have, let's say, let's make this one as a voltage source. So if we have, let's say, 3 volts, okay, as our voltage source, and then we have 1 amp, yeah, let's say we have 1 ohm right here, and then 1 ohm, okay, and then 1 ohm. Okay, so if you're going to add those, you'll get a total current of 1 ampere. Okay, so in here, we have a voltage drop. As you guys can see, if you're going to solve this one, we have a voltage drop of 1 volt. Okay, we have another voltage drop of 1 volt. And then we have a voltage drop of 1 volt. So as it goes back right here, it is now equal to 0. Okay, so that's why if you're going to add those three, 1 volt, 1 volt, 1 volt, it is equal to your main source of voltage. Okay, so there is no way that, like for example, you have 1 volt here, and then 0.5, nabura lahat. Let's say we have 0.5 volts right here, and then 0.5 volts right here. Okay, because this is already wrong, because if you're going to add those, you now have a total of 2 volts. Okay, so there is no other way that you'll get a voltage drop of 0.5 and 0.5 right here. So all of the voltages, I mean, all of the voltage drops, okay, if you're going to sum it up, it is equal to your original value of your voltage source. Okay, so that's basically it when it comes to KVL. Okay, so for you to be able to understand this one, so let's have this equation. So VAB plus VBC plus VCD plus VBA is equal to 0. So all you need to do is get the summation of all of those voltages and then equate that one to 0. Okay, that's how simple it is. All right. So for you to be able to appreciate this equation right here and then this equation right here, so let's have an actual example later on. Okay. But before that, uh, there's one more thing that you guys need to consider. Okay, when it comes to solving a uh, let's say Kirchhoff's law, okay, especially in KVL. So in here you can actually have a clockwise or anti-clockwise direction. So in here, the one that we have in here is the clockwise rotation, but you can also have the other way around, the anti-clockwise or the counterclockwise. Okay, so it's just that if your uh, assumption of your rotation is correct, then you will get a result of positive. Okay, that's always the case if you have the correct assumption of uh, rotation. However, if you've got the other way around, the incorrect rotation, so your answer is still correct. However, you will get a negative result. Okay, so if that happen, just make your result positive, and then reverse the uh, rotation of your first assumption. Okay, so from this into this. Okay, but if your first assumption is correct, then no need to change the polarity, okay, or the sign of your result, okay, because it will give you the same result, okay, clockwise or anti-clockwise. All right, so we have here the clockwise. We call that one actually we actually call that one conventional current. Okay, that's the technical term for that one. Okay, from left to right. And then we have the other way around, which is the anti-clockwise or the counterclockwise. We call this one electron current. Okay, because our current is flowing from the negative going back to the positive. So that's the reason why we call that one electron current. Okay, but nevertheless, let's say this is the negative way and then this is the positive way. Okay. So are we clear so far regarding with the two types of flow of current?
Yes, sir.
How about the others? So were you guys able to follow so far? Am I too fast or just fine?
Sakto lang, sir.
Okay. Okay. So I'm doing this one. I'll be fast since we have to finish two modules. Okay. And then I hope we can only have three meetings: part one, part two, and part three. But if it's not enough, then we'll be having a part four. Okay. Anyway, so let's now move on to the terminologies. Okay, when it comes to solving a Kirchhoff circuit law. So we have here the node, which we have already discussed a while ago, and then the path. I hope you guys are already familiar with path. Path is just a line. Okay, and then branches. So this might be new to you guys, and then loop. So this might be also new to you, and then meshes. Okay, so these terms are used frequently in circuit analysis, so it is important to understand them. So here are the definitions of those terminologies. So circuit, we have already discussed that one. Path, we're already done with this one. So it's just a line or a single line. Node, we are also done with this one. But for branch, so a branch is a single or group of components such as resistors or a source of which are connected between two nodes. So for you to be able to have a branch, so it must have a component between the two nodes. Okay, so later on we'll have a diagram for this one. And then a loop is just a simple closed path. So if there's a path that will lead you from the start up to the end, and then it leads back to the starting point, we call that one loop. Okay, so in a series circuit, so of course we only have one loop, just like this one. Okay, loop number one. If we have another circuit right here, let's say another resistor, then we have another loop right here, which is now called the second loop or loop number two. Okay, so that's it for the loop. For the mesh, so this one is kind of similar with the loop. Okay, but a mesh is a single closed loop series path that does not contain any other paths. So there are no loops inside the mesh. So let me just give you a real quick example comparing a loop versus a mesh. So let's have this as circuit. Oops. Let's have this circuit right here. Let's say this is your voltage source. This is your resistor, and then another resistor right here. So just a typical circuit, okay, parallel circuit. So I did mention a while ago that this is your first loop, this is your second loop, but you can also have a loop on the outside. Okay, so that is also possible. So all in all, we have three loops. Okay, so for the mesh, we can actually also call this one as a mesh. Well, that is actually the correct definition if it doesn't have a loop inside. Okay, so this is your first loop and then your first mesh also. Okay, so I'll call this one L and then M. So a loop and then a mesh at the same time. So this is your second loop. This is also your uh, loop, and then this is also your mesh at the same time. Okay, but for the third one, so let's say we call this one your third loop. This is just a loop. Okay, we cannot call this one a mesh. Okay, we cannot call that one a mesh because it contains another loop, okay, inside of it. So in this third loop, okay, it contains this first loop and then second loop. So if you're going to take a look on the meaning of the mesh, so it is a single closed loop series. Okay, so uh, for this one, we cannot call the third loop as a mesh. Okay, you can only call the first loop and then second loop as a mesh, but the third one, uh, not a mesh, just a loop. Okay, so are we clear with this one so far when it comes to loop versus mesh? All right,
Yes, sir.
so I hope you guys won't get confused when it comes to definition of loop versus a mesh. Okay, so here's a diagram when it comes to branch. So we have the node right here and then another node right here, and then it has a component inside. Then we can call this one as a branch. Okay, but in here we have a node, we have another node, but it doesn't have a component between it, so we cannot call this one as a branch. Okay, so we can only call it as a branch if it's between, or if there is a component between that two nodes. Like for example, this one, another node, and then it has a component inside of it, and that is also a branch. Okay, so this is also a branch. This is also a branch, but for this one, this is not a branch. Okay, the same with this one. This is not a branch. This is not also a branch. Okay, this is not also a branch. Okay, so are we clear so far regarding with branch? So it's very straightforward. So I guess uh, you'll be able to understand this one real quick. So clear or no when it comes to branch? What about the others? All right. So 2 out of 12. Okay, so I hope the others are also were able to get this one when it comes to branch. So here's more explanations when it comes to node and then a branch. Okay, so this is a branch AE, okay, or EA. AB is also a branch. Okay, from A going to B. BD is also a branch. Okay, B going to D. Okay, so you can also have two components actually. Okay, as long as it has a components inside of that or between that nodes. Okay, B going to D. Okay, so it passed through these 2 ohms and then 4 ohms. So that's also considered as a branch. Okay, and so on and so forth. Okay, so take note this one. This is not a branch, ED. Okay, because it doesn't have a component between it. And then for the loop, so we have here AB. C, D, and then A. So this is the loop. We could say that this is your loop one. We can actually have a loop right here, another loop right here, and then another loop right here, and then another loop for the outside part. Okay, so those are the loops. So question: how many loops we can form in here in this given circuit? Is it three? Is it four? Is it five? Is it six? How many loops?
6, sir.
Six. Who says six? How about five? How about four?
Four, sir.
Oh, what about the others? So six, four, ayun, finally. So the correct answer is five. Okay. So if you guys are going to take a look on this one, oops, what happened? So you can have a loop right here, first loop, second loop, third loop, fourth loop, and then fifth loop on the outer side. Okay, so that's why we have five loops. How about mesh? How many mesh do we have in here? Hello, hello. How many mesh? So we have five loops in total. But how about mesh? How many? Okay. So the correct answer is four. So very obvious. As long as it doesn't have a path inside it or another, a closed loop path, then that is already a mesh. So this is one mesh, another mesh, and then another mesh. So all in all, we have four meshes. But for this one, we cannot consider this one as a mesh because it contains those loops right here. Okay. Okay, so that's it for the definition of another definition for branches and then loops. Okay, so just note that components are said to be connected together in series if they have the same current. Okay, but for the other one, you could say that they are in parallel if they have the same voltage applied across them. Okay, so again, just reminding you guys the basic rules of electrical circuit, the Ohm's law. Okay, so another example of typical circuit. Okay, so loop, another loop right here. So your nodes, and then a branch right here, another branch, another branch, another branch, another branch, and then another branch. Okay, so let's have a example. Okay, with this one. Uh, but before that, since we don't have enough time anymore, so we will just continue this example on the part two. Okay, so goodbye for now, and see you guys later.
Yes, sir.
Okay, sige. Goodbye. Continue our discussion. Okay, so can you guys see my screen now?
Yes, sir.
Alright, let me just maximize this one. Okay, so let's have this example right here. So our main goal is to find the current flowing in the 40 ohm resistor R3. Okay, right here. So we can already identify the I1 and then the I2, but what about the I3? Okay, because we have two voltage sources right here. Wherein if you guys are going to take a look on this one, we have a current that will flow right here. Okay, and then another current that will flow right here. So if you're going to take a look at this one, so we could say that I1 plus I2 is your I3 right here. Okay, so that's basically our first assessment regarding with this uh, rotations of our loopings right here. Okay, okay. So let's have this solution. But before that, okay, we are going to have our own solution. Okay, because you might not be able to understand some of the solutions in there. Okay, so with this one, our first uh, thing that we need to do, okay, is the KCL. Okay, find the KCL equation. Okay, So you can actually have a KCl on this node, or you can have a KCl on this node. But mostly, we always deal with the KCl on the superimposed node. Super node. Okay, not superimpose. We always try to find the super node. Okay, so this is a node, this is a node, this is also a node, and then this is also a node. But when we say super node, that node is the main node that every current that will flow into. Okay, so you can actually consider this one as a super node also, but we'll just deal with one because even either of those two, okay, even you consider this one, it's still the same. Even though you consider this one, it's still the same. Okay, so let's just deal with one super node. Okay, let's say super node A. Okay, so if you guys are going to take a look at this one, this node, we have a node entering I1, and then we have another node entering I2. Okay, which is this one, and then which is this one. Okay, and then we have another current, of course, that will leave that node, which is now the I3. Okay, which is now this one right here. Okay, so again, going back to our KCL, so when we see entering, it is positive. Okay, so I1 is positive, the same with I2. Okay, but if it's leaving like the I3, then that should be negative. And then after that, equate that one to 0. Okay, so did you guys get this one so far? I1 plus I2 minus I3. Hello, hello.
Yes, sir.
Are we clear so far with this I1 plus I2 minus I3?
Yes, sir.
Okay, so I'm just checking because this is a very crucial explanation. Because if you won't be able to understand this example number one, then there is no way that you'll be able to understand the following examples. Okay, so in this one, in this equation, let's see, this is our equation number one. Okay, we can actually come up with a simplified version of this one wherein we can transpose this negative I3 on the other side. Okay, so we could have I1 plus I2 is equal to I3 instead, just to eliminate that 0 right here. Okay, or you can have the I3 is equal to I1 plus I2. Okay, so this is now our official equation number one. Okay, so let me just highlight this one because this is the one that we will use later on. Okay, so after KCL, then we can now apply KVL. Okay, so remember that in KVL, so as it passed through a certain uh, say load or resistor, you'll get a voltage drop. Okay, so knowing that it will give you a voltage drop, okay, so those should be, or yeah, those resistors should have a label of negative sign. So how do we do that? So you can come up with this kind of scenario. So this one is negative, of course, and then this side of your voltage source is positive. Okay, and then in here we have here positive and then negative. So later on I will explain why we have positive and negative, not negative and then positive. So the same with this resistor right here, we have positive and then negative. Okay, so if you guys are going to take a look on this, uh, uh, let's say loop one right here, let me just isolate this one for now to avoid confusion. Okay, so let's just have a series connection. Okay, so we only have one loop. Okay, and then you'll have a voltage drop right here and then another voltage drop, and then as soon as you go back right here, if you're going to sum up those two voltage drop, you'll get 10 volts. Okay, so that's basically the idea when it comes to KVL. Okay, so to have a KVL, so first is the voltage source first, which is 10 volts. Okay, so I will get the sign, okay, or the polarity, okay, or the what do you call this one? Yeah, sign. Okay, this positive sign right here. So the outer part of this component. So I will get positive 10 volts. Okay, followed by, okay, this voltage drop on the R1. So how do we get the voltage drop on the R1? So going back to our equation, so we have V1 is equal to I1 times R1. Okay, so that's basically the equation that we're going to use on how to get the voltage drop on the R1. So in here, since we know that we're going to have a voltage drop, so it will not be added to our voltage source. Instead, it will be deducted to our voltage source. Okay, so that is why we have to consider the outer part. So if you're considering the outer part, then you have to stick with the outer part. If you're going to consider the entering part, this one right here, the negative, then you have to stick with the entering part. So either of those two, you will get the same answer, okay, as long as you're consistent, okay. So in here, I always use the outer sign on how to, finalize my signage. So in here we have positive 10 volts, and then in here we have negative I1 times R1. Okay, since we are getting the voltage drop across R1, followed by the R2 right here, which is now the I3. So we will have negative, okay, so positive and the negative, I'll consider the outer sign, negative I3 times R2. So I3 rather, since this is resistor 3, okay? And then after that, going back to our voltage source, original voltage source, just equate this 1 to 0. Okay, so this is now our equation number 2. Okay, this equation number 2 came from loop number 1. So are we clear so far on how did we get this equation right here? So basically we could call this one KVL. Let me just remove this one. KVL at loop number 1. Okay, this equation right here. So were you guys able to follow so far on how did we get this equation? Okay, what about the others? So let me know if you are confused. So this is a very crucial example. So again, if you will not be able to get this one right now, then there is no way that you'll be able to get the following examples. So we have 3 more examples later on. So please let me know if there's a part that you wasn't able to understand, okay? So this is now our loop number 1, and we can now replace our variables, wherein let's say R1 is 10 and then R3 is 40 ohms. Okay, so we have 10 volts minus I1. Okay, R1 is 10 ohms, so I1 times 10 minus I3, and then R3 is 40 ohms, equal to 0. Okay, so this is now our updated equation number 2. So we can keep that one as it is already. Then we can now proceed to KVL at loop number 2. Okay, so in here, of course, we are now going to consider the right side equation. So still the same, we have to label the polarity. So we have to consider this polarity right here. So negative, positive. So the flow of current is from here to there. So of course, as it passes through this resistor right here, it will give you a voltage drop. So I will put here the positive and then negative right here. And then another positive and then negative right here. Okay, and then as it goes back right here, just equate that 1 to 0. So again, I always consider the leading part or leading sign. So we have here positive 20 volts. Okay, then of course it's now minus since we have a voltage drop on the R2. R2. So this one will become I2 times R2. Okay, or we can already write the value of R2, wherein the value of R2 is 20 ohms. Okay, followed by the other voltage drop on the R3. So minus I2 times R3 is 40 ohms, equal to 0. Okay, so this is now our equation number 3. Okay, so were you guys able to follow so far? And how did we get the equation number 3. So KVL at loop 2. Hello, hello, hello. Okay, so let me guys ask you one by one. So let me know if you guys really were able to get this one. Mr. Carlo, are you there?
Yes, sir.
So were you able to follow up to this point? This third equation?
Medyo ginagamay lang ako, sir. Medyo hindi ko po magets.
Okay. Okay, so at least it's an honest answer. How about Mr. Francis?
Iniintindi ko pa po, sir.
Okay, Mr. Maaba? Okay, maybe he's not around. Mr. Nathaniel?
Na-analyze po, sir.
Okay, how about you, Miss Leah?
Ina-analyze pa po, sir.
Okay, Mr. Jason?
Na-analyze pa po.
Okay, Mr. Sajin?
Ina-analyze din po, sir.
Okay, Mr. Isagani? Mr. Isagani? Okay, maybe he's not also around. Ah, okay, so gets niya, yata, I think. Okay, how about you, Mr. Aaron?
Same here, sir. Ina-analyze din.
Okay, Miss Grace?
Still analyzing, sir.
Okay, Miss Sophia?
Ina-analyze po, sir.
Okay, Mr. Cameron?
Sir, analyze pa po.
Okay. So, to make it quick, just give me a thumbs up if you guys were able to get this part. So let's start with the KCL. So give me a real quick thumbs up. 5, 4, 3, 2, 1. So dalawa, tatlo, apat. So apat lang yung nakagets for this equation number 1. On how did we get this one? 5, I guess. Okay, so maybe at least half of you guys were able to get this one. How about loop number 1? Okay, or equation number 2? And how did we get this equation number 2? So 1 only. Dalawa. Okay. So hindi na ako magtatanong sa loop 2. I think si Mr. Isagani lang yung nakakuha nito. Anyway, so let's start with the equation number 1. Okay, so let's start from the scratch. So let me get this one again, so that you guys will be able to get this one, fully understand everything. Okay, so again, when it comes to KCL, okay, we always try to find the supernode. Okay, when I say supernode, it is a part wherein most of our components are connected with. So in here, this node right here is connected with this R1, it's connected with R2, and then the R3. And then the rest, so most of them just have two components on this path and then this path. But for this one, it has uh, 3 branch to be exact. Okay, so the more branch that that node is connected, then that's the more reason why you call that one super node. Okay, and then the rest are just normal nodes. So we could say KCL at loop A. So again, if it's entering, okay, if it's entering a node, that's positive. Okay, but if it's leaving a node, then that's already negative. Okay, that's the signage that you guys have to follow when it comes to forming an equation when it comes to KCL. So KCL at loop A, as you guys can see, we have I1 entering, I2 entering. So that's why we have I1 is positive and then I2 is also positive. But for this one, so it's now leaving our node A. So that's the reason why we have to put here negative I3. Then after that, just equate everything to 0. And then from here, you can transpose this one on the other side, wherein it will give you this equation. I3 is equal to I1 plus I2. Okay, so this is now our equation. Why is it lagging? Equation number 1. Okay, so I hope you guys were able to get this one. So let's now move on to the KVL at loop 1. So where is our loop 1? So here's our loop 1. So the second thing that you guys need to do is label, okay, or put the signages, okay, of our components. So we have here the negative and then positive, okay, and then we have here positive and then negative. So let me just explain, just in case that you guys were able to uh, made the incorrect signage, let's say negative and then positive. So right here, as you guys can see, if we are going to follow the outer signage, we will get positive 10 volts, positive 10 volts, okay? And then at the same time, we will also get positive I1 times R1. So remember, as our voltage source will pass through a load or a resistor, it will give us a voltage drop. But in here, the one that is happening, it's like, we have another voltage source right here wherein they are being added with each other. Okay, so we could not say that this is a voltage drop anymore since it has a sign of positive. So that's the reason why the correct uh, polarity with this one, wala na yung okay, right here. So the correct polarity with this one, or the signage for this one, so this one must be positive and then negative on the other side. Okay, so the same with the R3, positive and then negative, because we must have a negative signage after passing through a certain load or resistor. Okay, so in here we have positive 10 volts minus, okay, I1 times R1 because this is a voltage drop, and then another voltage drop right here, minus I2, I1, and then I3 equal to 0. So when it comes to, dealing with loops, especially in KVL, so just consider this one loop right here. So that's why I separated this one a while ago on the other side. Okay, so you can just focus with the left side part. Okay, instead of looking at both uh, loops. Okay, so just focus on loop 1 since you're dealing only with loop 1. And then in here you can now substitute the given values. So we don't know the value of I1, so just leave it as I1, and then R1 is 10 minus I1, and then R3 is 40, then equal to 0. So this is now your final equation number 2, since we cannot do any simplifications with this one anymore. Okay, so uh, I hope you guys were able to get this one now. So just give me a thumbs up if you guys were able to get the equation on loop number 1. Okay, so at least there's now 3, I guess. 1, 2, 3, or 4. Okay, so that's it for the equation number 2. So just leave it as it is for now. So let's now move on to KVL. Okay, at loop number 2. Okay, this one now on the right side. So we have here again the negative and then positive, positive, negative, positive, negative. Okay, so in here we have positive 20 volts followed by the voltage drop on the R2. So I minus I2 times R2, and then minus, okay, since we're dealing with the outer signage, minus I2 times R3, okay, equal to 0. So after that, you can now substitute the given values of your R2 and R3. So 20 minus I2 times 20 minus I2 Oops, my bad. This is not I2. This is I3. Okay, because we have the I3 right here. But for this one, yeah, I1 and then I3. And then this one, I2 and I3. So this one is yeah, I3 and then I3 and then R3. So this is 40 ohms equal to 0. And equation number 3. Okay, so were you guys able to follow with this equation number 3? Hello, hello. So how many of you now were able to get this one? Dalawa pa din? Tatlo? So at least there's now 3. Before, there were only 2. Okay. So we have an additional 1. So I hope the others were now at least able to get at least 70 to 80%. Okay, on how did we get this equation number 3. But anyway, so after getting the Kcl equation, KVL, and loop 1 and loop 2, so you now have a total of 3 equations. Okay, so the thing that you guys need to do is, try to find the value of your I1 and your I2 and then I3. Okay, once you were able to get that one, then you can now find the voltage drop on the R2, voltage drop on R3, on the R1, etc., etc. Okay, so our goal in this one is find the current flowing on the 40 ohm resistor. So we should be able to find the value of the I3 right here. Okay, so in order to do that one, so we have to use this equation number 1 right here. So in here, we have to know the value of your I1 and then the value of I2. So once we learn the value of those currents, then we can now solve for the value of I3. Okay, so in here, we can actually use this equation number 3 and number 2 for us to be able to solve one variable. Okay, but before we can do that, if you guys are going to take a look on our missing variables, so for the equation number 2, we have the I1. Oops, my bad. So this is not I1. Okay, so this is I3. Okay, because we have the current on this RT right here. Okay, so this is the I1 and then this is the I3. So let me just change this one, okay, into I3. Okay, so in the equation number 2, we have two missing unknowns, the I1 and then the I3. And then for the equation number 3, we have two unknowns also, which is the I2 and then the I3. Okay, so just by getting those two equations, we now have a total of 3 unknown variables. Okay, but we can eliminate that one into 2 just by substituting the value of this I3 right here onto our equation number 2 or equation number 3. So let's say we have to substitute or replace the I3 into this new equation I1 plus I2. So from equation number 1 to equation number 2. Okay, so we're going to use this one as our value of our I3. So 10 minus I1 times 10 minus, so our I3 is equal to I1 plus I2. So we're going to use that one, minus I1 plus I2 times 40. Okay, equal to 0. So were you guys able to get on how did you get this equation right here? So we've just simply replaced the value of this I3 into I1 plus I2. Okay, so with that, we can now have two unknowns, okay, which is the I1 and I2. So after replacing this I3 also, we're going to have two unknowns in total. Okay, so before we have three unknowns, but after substituting the value of equation number 1 into equation number 2 and equation number 3, we can now have two unknowns only. Okay, so all you need to do is eliminate or lessen the unknowns, okay, for you to be able to get the say one unknown into second unknown and then up to the third unknown. Okay, so we have to do that one by one. Okay, so in here we can simplify this one a little bit more into 10 minus I1 times 10 minus I1 times 40, okay, minus I2 times 40 is equal to 0. So just add or combine similar units. So 10 minus, so minus I1, and then we have minus I1 here. So 10 minus 40, or my negative 10 minus 40 is negative 50. I1 times 50 minus I2 times 40 is equal to 0. And then you can now say that this is your equation number 4. Okay, the newly formed equation number 2. Okay, so do the same thing on the equation number 3. So equation number 1 going to equation number 3. Okay, so we have 20 minus I2 times 20 minus, so our I3 is I1 plus I2. I1, so minus I1 plus I2 times 40 is equal to 0. Okay, and then just simplify this one a little bit more. So this one will become 20 minus I2 times 20 minus I1 times 40 minus I2 times 40 is equal to 0. So this one will become 20 minus, so we have 2I2, so 20 plus 40. So I2 times 20, 60. 20 plus 40 is 60. And then minus I1 times, what is this? 40. I almost thought that that was 10. Okay. So sorry for my, ugly handwritten since I'm only using my mouse. Equal to 0. So from here, we could now say that this is your equation number 5. Okay. So were you guys able to follow up to this point? So for the equation number 4, I just simply replace the I3 into I1 plus I2. Okay, right here. And then just simplify and then combine two similar units. And then you will get this one as your final equation for number 4. The same with the equation number 5. So I just simply get the equation number 3. Okay. Oops, equation number 1. And then replace the I3 into I1 plus I2. Okay, and then you will get this one as your new equation. So you could say that this is your equation number 5. So from here, we can now actually use this equation number 4 and 5 to eliminate one of the variables. Okay, so the one that we're going to use right here is called the simultaneous equation process. Okay, so from here, we're going to get the 4 and 5. Okay, so what we can do is I will just copy this one and paste it right here. Let me just remove those unnecessary text. So we now have this equation number 4. And then I will also get this equation number 5. Oops, redo. This equation number 5 right here. So let me just remove the unnecessary text. There you go. And then I will combine those two. It's like, we're going to add them. So in here, we could actually add them already But before that, we have to multiply a certain value for us to be able to eliminate one variable. So if you want to solve for the, oops, my bad. So let me just arrange this one so that I2 and I2 is, aligned with each other, and then I1 and I1 is aligned with each other. So let me put this one right here, and then this one on the other side. Okay, so I2 and I2 now is aligned. I1 and I1 now is also aligned. So in here, we can 4, 8, 12, 40 times 4 times 5. So we can multiply the equation number 4, okay, into times 4, and then we can also multiply the equation number 5 into times 5, okay. So we can do this one since we multiplied everything, kids. So we didn't change anything, okay. So what we wanted to uh, attain is we have to get a value of 200 right here, and then a value of 200 also right here, okay. uh my bad. So if you're going to add them, it will just become 400. Why do we have same polarity or same minus minus? Okay, so instead of adding, we can actually change this one into subtraction. So it's also possible. Okay, so that this one will become a positive. So negative 200 plus 200 will become 0. Okay, so in here, if we are going to multiply this one by 4, we will get 40. Okay, but I think we don't have enough time anymore. Anyway, so we will just continue this one on the part 3. So goodbye for now, since we don't have enough time anymore.
Yes,
And then
sir.
let's just meet again on the part 3. Okay,
Yes, sir.
all right. Okay, so hello again. So again, before we continue our discussion, so let me just check if you guys are already ready or in front of your computer. So just give me a thumbs up. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Great. So most of you are already here and ready. Okay, so let's now continue this one. So again, just multiply this equation to 4. So 10 times 4 will become 40. And still a negative minus I1. So 4 times 50 will become 200. And then still negative minus I2. And this one will become 160. So 40 times 4 is 160. Okay, equal to 0. So this is now our equation number 4. Okay, so for this one, this equation number 5, just multiply this one to 5. Okay, so 5 times 20 will give us 100 minus I1. So 5 times 40 is 200. Okay, minus I2. So 5 times 60 is 300, is equal to 0. So this is now our equation number 5. Okay, so were you guys able to follow so far? And how did we get those equations right here? Equation number 5. Okay, just one. What about the others? Okay, great. And then we can multiply this one okay, into negative, or we can just simply, deduct this one so that we can have 40 minus 100 will give us negative 60, and then minus plus minus, okay, will become positive. So all in all, this will become positive I1 200. So this will be cancelled. Okay, it will give us a 0. And then in here, so negative plus negative will become positive. So positive 300 minus 160 is equal to positive 140. 140 is equal to 0. Okay, so we could now call this one as your equation number 6. Okay, and then in this equation number 6, we can now solve for the value of your I2 since we now have only one unknown. So this one will become negative I60 plus I2 times 140 is equal to 0. Okay, so just transpose this negative on the other side. So it will give us I2 times 140 is equal to 60. Okay, and then simplify this one a little bit more just by putting this one on the other side. So this one will become I2 is equal to 60 divided by 140. So using your calculator, I2 is equal to 60 divided by 140. It will give us a result of 0.428. Okay, or 429 rather. You're going to uh, round up the 8 into 9. Okay, so 429 ampere. So this is now the value of our I sub 2. So were you guys able to get this one? And how did we get the value of I2?
Yes, sir.
Okay, great. So we now have the I2. So we can now also eliminate the I2 right here for us to be able to get the value of I1. So how do we do that one? So we can do the same method. So we have to make this one equal to this one. So to do that, so we have to multiply the equation number 4 to 3 and then equation number 5 to 2. So 2 times 6 is 120 and then 3 times 4 is 120. So for the equation, let me get this one. And then let's place it right here. Simultaneous equation for the 4 and 5. Still 4 and 5, but in here we now have to eliminate the I2 for us to be able to get the value of I1. So in here, this will become times 3, and then the equation number 5 will become times 2. Okay, so doing that one, our equation number 4 will become 3 times 10 is 30 minus I1, 50 times 3 is 150 minus I2, 40 times 3 is 120 is equal to 0. Okay, so this is now our equation number 4. So just let me know if I did something wrong. Okay, and then for the second equation or the equation number 5, so just multiply this one into 2. So 20 will become 40 minus I1 times 80 minus I2 times 120 is equal to 0. This is now our equation number 5. Okay, and then we can now deduct this one for us to be able to eliminate this I2 right here. So negative 40 plus 30 is negative 10, and positive 80 minus 150 is negative I1 times 70. Okay, and then this one will now be eliminated, of course, since negative 120 plus 120 is equal to 0, and then equal to 0. So now is your equation number 5. Okay, so again, you can now simplify this one a little bit more for you to be able to get the value of I1. So just transpose this one on the other side. So I1, see, so we can also do that one. Next, let's just make this one positive I1. I1 times 70, okay, is equal to negative 10, since the one that we transpose is this expression right here. And then from here, I1 will become negative 10 divided by 70. So I1 is negative 0.7 ampere. Okay, so as you guys can see, we've got a value of negative in here. It only means that our assumption on loop number 2 is incorrect. Okay, so our loop right here should be clockwise, not counterclockwise. Okay, so we have a loop clockwise and then another clockwise right here. So that's the correct rotation of this current right here. So in here, if you've got a result of negative 0.7, then this one is still correct. Okay, just make this one positive and then just change your polarity from counterclockwise into clockwise. Okay, so no need to worry if you've got a value of negative. It only means that you have an incorrect assumption of loopings. Okay, so are we clear so far on how did we get the value of I2 and I1?
Yes, sir.
Okay, great. So going back to our first equation, equation number 1. So as long as we know the value of I1 and I2, then we can now solve for the value of I3. So since we now already have the value of those I2 and I1, then we can now solve for the I3. So I1 plus I2. So I1 is negative 0.7, okay, plus I2 is 0.429. Okay, so take note, you still have to, get the signage. Okay, do not make this one positive yet. So I3 is now equal to, so negative 0.7 plus 0.429 will give us a result of negative 0.271. Okay, so once you've got already the all of the values of your currents, and that's the time that you can now change this one into positive. So I3 now is equal to 0.271. Okay, so meaning this I3 right here is also incorrect. Okay, so instead of leaving, this one is actually entering. Okay, so that's the correct assumption when it comes to this polarity of I3. So we have I1 entering, I3 entering, and then I2 leaving. So that's the correct assumption when it comes to those currents. Okay, so voila, we now have the result for the I3. So the correct answer for this 40 ohm resistor, okay, so the current that is flowing is 0.271 ampere. Okay, and if we are going to compare that one with our solution, so in here we have two super nodes, but either of those two, they are just the same. Again, just like what I mentioned a while ago. So at node A or at node B. So it will give you this equation right here, wherein they are just the same. And then we have those three loops, okay, which is the same with what we have. Okay, just analyze this one again. And then in here, we've replaced the, let's say this, where is that one? This I3. Yeah, this I3 right here into a I1 plus I2. And then got this new values right here, or this newly expression, and then you can now use those expression for you to be able to get the value of I1 and I2. But in here, I didn't use simultaneous equation, but I did use the calculator. But of course, you can use that one just like what we did a while ago in here. This is the longer method, simultaneous equation 4 and 5, simultaneous equation and 4 and 5. Okay, but if you want to do the short method, okay, so as long as you know the final equation of your this one and this one, then you can now use that one and then use your calculator for you to be able to get the I1 and I2. So just look for the function. Uh, where is that one? Look for the function So in my case, I'm using the Casio FX991EX, and then just by clicking the mode or setup, I can find here the equation or func, F-U-N-C, okay, or function. Okay, so just go over on that one. Okay, and then you'll be given a choice as we're in to give a simul equation, and then the other one is polynomial. So just choose the simul equation, and then after that you will choose how many unknowns that you have on that equation. So since we only have two unknowns, the I1 and then the I2, then I will choose two unknowns, and then it will give you this. So of course you guys cannot see. However, I have a demo, I guess, in here. Mm, 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 mm. I think I wasn't able to put a demo. Okay, let's just find it on YouTube. So how to use simultaneous equation in calculator. So of course we have different versions of calculator. Just find for the specific version of your calculator. So you can find here the 991ES or the 991EX, which the one that I have in me right now. So let's go over with this one if you have this kind of calculator. So for example, you have this equation right here, equation number 1 and equation number 2, and then you also have two unknowns, the x and y, and then x and y. So just click mode and then click number 5 for the EQN or equation. And then we have here four different syntaxes. So since we only have two unknowns, you have to choose the number 1. ENX plus BNY is equal to CN. So this is your ENX, and then this is your BNY, and then this is your CN. If you're going to choose the number 2, meaning you have three unknowns, okay? The A, B, and C. All right. And then the rest are another format or syntax, but mostly you're only going to deal with two unknowns or three unknowns. Okay, but you can have up to four unknowns. Okay, just by choosing the number 4, I guess. By the way, can you guys hear what is my screen saying? Can you guys hear anything?
No, sir.
Wala, wala. Okay, so I think it's right here. Well, anyway, so just watch this one, just find it on YouTube. So how to use simultaneous equation in a calculator. So after clicking the number 1, it will give you this one. So just click the value of your the first value, which is 3. So 3 and then equals, and then the second one is -2. So you have to negate that one also. -2 and then equals. Okay, and then the last one is +6. So 6 and then equal. Okay, so do the same on the second equation. So 5 equal, and then it will give you to the it will lead you to the second expression, which is the letter B. So +6 equal, and then the last one is 38 and then equal. Then after that, if you're going to press equal, it will give you the values of your x and y. So in here, the solve value from the calculator, x is equal to 4, and then y is equal to 3. Okay. So I would like you guys to do this one also, because this is the faster method, actually the fastest method, okay, by using the calculator, okay, as long as you have the correct equation, of course, then you'll be able to get the value of those unknowns, the I1 and then I2 right away, okay. So I will leave this part to you guys, since I'm not sure which calculator you're using. So you guys have different versions of calculator. So you're the one who's responsible to find a specific tutorial on how to use the equation on that calculator of yours. Okay, and then after that you will get these results right here. Okay, so we have here the I1, which is negative 0.143. Let's compare it. Oops. And then the other one is 0.429. 0.429. And why did we get a different result in here? Negative 0.143. But we've got the correct answer, which is 0.271 or the 0.28. Just has a little variation. Okay, 0.286. So I think the assumption right here, or the the polarity of the one that they've used, is the uh, entering part, or the entering symbol, which is the negative, and then this one will become positive, and then this one will become positive again. So negative, positive, positive. Either of those two, so you will get the same correct answer, okay, which is 0.286. So since we have two different results, wherein I've got negative 0.7 and then the other one is the same, which is 0.429. Okay, so I would like you guys to recheck, okay, uh, what differs with my solution right here and then my solution right here right now. Okay, well, anyway, since we don't have enough time anymore, and then we cannot go back in here and then analyze everything again, so I will leave this one to you guys. And then if you want to get the voltage drop across RT, then just get the value of that I3, which is 0.286, and then the resistor on that I3, which is 40 ohms, and then you will get 11.44 volts. Okay, so yeah, that's it for the example number 1. So any questions so far?
Answer.
Okay. So I hope the others were at least able to get 50% of the idea or the process, and how did we get the 0.286 right here. Anyway, so that's it for the example number 1. So here's just a more explanation on how you execute the process of Kirchhoff's circuit law. So the first one is the most common thing that we do, but either of those step 1 or step 2, so uh, you can interchange those two, okay, as long as you have already mastered the things that you guys need to do, especially in solving the Kirchhoff's circuit law, okay, or Kirchhoff circuit diagram. So in here, you will just assume all voltages and resistance are given. If not, label them V1, V2, R1, and R2. But in our case, it's already given, so we don't need to do that one. Okay, so that is why we have already jumped onto the number 2. Okay, but in here, it's also already given the clockwise or the anti-clockwise. So step 1 and number 2 is already done. And then step number 3, so label each branch with a branch current. So in here, it's also done, which is the I1, I2, and I3. So they are already labeled. And then the things that we did now, which doesn't exist in here, okay, is the KCL, which is now step number 4. And then after KCL, it's now the KVL. Okay, and then after finding the equations, equation number 1, 2, 3, and 4, or how many equations that you can now try to eliminate some of the equations by using the simultaneous equations, okay, to solve the unknown variables. Okay, so yeah, you can do any of this one right here. So the important process right here, you have to do the KCL first before the KVL. Well, actually, you can do also KVL first before the KCL. So there is no, you know, uh, absolute process or step when it comes to solving a Kirchhoff circuit law. Okay, as long as you know what you're doing, you can do any step right here first. Well, except the step number 6. You cannot do a linear simultaneous equation if you don't have the given equations. Okay, so that's why you have to do the there's first 5 steps before you can do the step number 6. All right, so that's it for the process. So here's more explanation when it comes to using Kirchhoff's circuit law. So again, we have this law right here is for us to be able to calculate the various voltages and currents circulating around a linear circuit. So we can also use loop analysis to calculate the currents in each independent loop, which helps to reduce the amount of mathematics required by using Kirchhoff's laws. Okay, so this one is super similar also with the Ohm's law. So whatever you can do in Ohm's law, you can also do that one on the Kirchhoff circuit law. So you can find the individual voltage drop, individual uh, current, etc., etc. Okay, just a different method. So the same with this one. So I will skip this one since this is just another explanation how to use or how to apply KVL or KCL on a complicated circuit. So let's have this second example now. So in here, where is that question? Okay, but the question right here is we have to find the individual voltage drops, okay, and then the individual currents at the same time. I1, I2, I3, I4, and then I5. Okay, so if you guys are going to take a look at this one, we can easily combine this one using the parallel uh, circuit law. The same with this one, the parallel circuit law. And after that, you will have a single series path or single series circuit diagram. Then after that, you can now find the I total. Okay, so that's the way wherein for you to be able to verify what is the value of your I total. You can also apply the KCL right here. Okay, so if you guys are going to take a look on this one, you can apply it on this part or on this part. Okay, so we have I1 and I2 entering. Okay, and then IT which is leaving. So of course I1 plus I2 is equal to IT. So the same with this one on the right side. So we have IT entering on this node right here, and then we have I3, I4, and then I5 leaving. So if you're going to analyze this one, also we have IT as your positive, and then I3, I4, I5 as your negative. So of course, if you're going to divide this one into 3, it is still the same if you're going to add those 3 individual currents right here. Okay, so those are the ways. But in here, what we simply did is we combine these two and these 3 into one value. Okay, so this is the computation for the RAC, and then this is the computation for the RCF. So after that, we can now get the total resistance. So 1 plus 10. Okay, so that's your total resistance. So that is why we have RT is equal to 11 right here. And then for the VT, we have 132 volts, which is the original voltage source right here. So since we are getting the I total, so we have to get the total values of your voltage and then R total. So 132 divided by 11, you'll get 12 ampere. Okay, so that is now the value of your IT right here. So after that, you can now have this one, of course, after simplifying or getting these values right here. So we have I total 12 ohms. The first one is 1 ohm. Second one is 10 ohm. Okay. And then after that, you can now solve for the individual voltages. Okay. So in here in the RAC, of course, we only have one voltage that is flowing since they are in parallel connection before. The same with the RCF, those 3 branch, we now have a single voltage value. So that is why if you guys are going to take a look on this one, I1 and I2, we have the same numerator. So that is the voltage that is flowing on the I1 and I2. And then for the I3 up to I5, we also have a single value for voltage since they are in parallel. So now, how did we get those 12 right here and then 120 right here? So this one came from this circuit right here. So remember how to get the oops, how to get the individual voltage. So for us to be able to get the individual voltage, so we have to use this formula. V1 is equal to I1 times R1. Okay, so I1 is equal to your IT, since we now have a series connection, which is 12 amps. R1 is 1 ohm. So V1 now is equal to 12 volts. Okay, so this is now the value of your RAC, or V1 and then V2. Okay, so that is why we have the same value of your I1 and I2 for the voltage across them. So V1 is 12 volts, and then V2 is also 12 volts. So that's it for this part right here. Okay, and then for this part, so the same concept. So we have V2, let's say this is your second voltage drop, is equal to I2 times R2. Okay, let's just say that this RCF is your R2. So I2 is still 12 amps, okay, since again we have a series connection. So all of your values of your currents are the same. So V2, why is it lagging? V2, so I2 is 12 and R2 is 10. Okay, so V2 is now equal to 120 volts. Okay, so this one is also the same with, my bad. So let's just make this one V3. Okay, and then this one is R3. V3. So this one is equal to your V4 and then V5, since we have three branches on that one. Okay, so your V1, V2, V3, V4, and then V5. Okay, so 12 volts for the V1 and V2, and then 120 volts for the V3, V4, and then V5. And then just substitute that one using these formulas right here, and then you will get those individual currents. So 12 divided by 2.4, which is the R1, you'll get 5 amp, and so on and so forth. Okay, and then using the KCL for you to be able to verify if your results right here are really correct or no. So you can have this one. Okay, so I total is equal to I1 plus I2, which is this one, or you can have the I total is equal to I3 plus I4 plus I5, which will be coming from here. Okay, so I1 plus I2, 5 plus 7, so that's equal to 12. So that's actually correct for the values of I1 and I2. How about the I3 and I4 and I5? So 2 plus 6 plus 4 is also equal to 12. So with that, you have already verified that your values of your I3, I4, and I5, and then I1 and I2 is actually correct. Okay, just by using the Ohm's law in here. And then this one is with the use of the KCL. Okay, so are we clear so far? Were you guys able to follow? What about the others? Okay, 80%. Okay, so you might get somehow lost. Okay, especially if I didn't show everything. But anyway, as soon as you're going to review this one, you'll be able to understand everything, hopefully. Okay, just by reading everything in detail. Okay, this one, the explanation, and then this circuit right here, and then those more explanations, and then the you know computed values, etc., etc., and then how to check it using KCL, and then more explanations, etc., etc. Okay, but anyway, that's it for the example number 2. So let's now move on to example number 3, since we don't have enough time anymore. So in here, find the currents flowing around the following circuit using Kirchhoff's current law only. So take note, we only have to use KCL, okay? So we can actually use Ohm's law right away right here, just by combining those two using the parallel law or parallel rule circuit. But since we are restricted to that one, so we have to show the Kirchhoff's current law, okay? But before we can do that, we have to apply KVL also at the same time. Okay, so let me just get this one. Okay, so in applying a KCL, so that's super simple. So we can actually find the Kcl equation right here, since we have entering and then 2 leaving. Okay, so just find the node wherein there is a current that is entering and then a current that is leaving at the same time. Okay, so that's the way for you to be able to know where to start doing your KCL equation. So KCL at node B. Okay, so in here we have I1 is positive minus I2 since they are this one is leaving, and then the same with I3 since that is also leaving. So if you're going to simplify this one a little bit more, it will give us I1 is equal to I2 plus I3. So this is now our equation number 1. Okay, so clear so far on how did we get this equation number 1? I1 is equal to I2 plus I3. Okay, so super simple. The next one after KCL is now, of course, the KVL. So we can have a loop right here inside. Let's call this one loop number 1, or loop on the outer side. Okay, let's call this one loop number 2. So let's start with KVL at loop number 1 first. Loop number 1. So in here we have, of course, this one is negative, positive, and then this one is positive, positive, negative, positive, negative, and then positive, negative. So loop number 1, so we have positive 12 volts going here, we have negative, okay, I1 times R1, negative I1, so R1 is 4, I'll put here the value already so that we can have a lesser, you know, uh, equation. And then in here, going here to here, so we now have negative I3 times R3, which is 12 ohms. And then going back to our voltage source is now equal to 0. Okay, so that is now the KVL at loop 1. So we cannot simplify this one any further since there is no similar units. Equation baliktad, EQN number 2. Okay, so did you guys get on how did we do the equation number 2? Are we clear so far? Okay, it's 1, 2. Okay, so this is just the equation, I mean KVL at loop number 1. But how about the KVL at loop number 2? KVL, why is it lagging at loop number 2? Okay, let me just encircle this one for consistency. So in here, we're still going to use this one, and then we're still going to pass through this R1, but we are now going to pass through the R2 and then going back right here. Okay, so that's what will happen for the loop number 2. So we still have positive 12 volts minus I2, I1 first. I1 right here times R1, which is 4. And then going right here, we now have minus I2 times 6 ohms. And then going back to our original voltage source, it is now equal to 0. Okay, so we now have equation number 1, equation number 2, and then equation number 3. So did you guys get this one so far? And how did we get the equation number 3? Okay, so from here, again, you can now use this one to replace the value, I mean the variables on the equation number 2 and then equation number 3 for you to be able to get the I2 and I3 variables only. Okay, sorry, it is not the I3 right now, but it is the I1 that you have to replace. okay, for you to be able to get the I2 and I3 on the equation number 2, and then I2 and I3 on the equation number 3. Okay. Okay. All right. So let's now continue this solution of ours in example number 3. So let me just check if you guys are already in front of your computer. So just give me thumbs up. Mhm. Okay, great. So as you guys can see, after forming these equations right here, so it is now completely to you which process you're going to use. Is it simultaneous equation or via calculator? So either of those two, it will give you the same answer as long as you have the correct, solution or correct expression or equation. Okay. So in here, I will not solve this one anymore since we don't have that much time anymore. And we are still at slide 29 and then we still have more slides. So I think we cannot finish the the third module already. The fourth module rather, since this is, uh, ah, sorry, this is the module number 1 and 2. My bad. This one was supposed to be module number 3. Yeah, that's correct. But why is it module number 2? Why is the name of my... Anyway, this one is module 3. Okay. And then the next one is module 4. So for the third example, where is that one? So you will get this equation right here for the ABC, the outer loop. And then for the ABD, you will get this one. So let's compare if they are the same. So equation number 1, okay, which is this one, so 12 minus 4I1 minus 12I3, which is correct. And then for the second equation, the outer part, so we have here 12, okay, which is already transposed on the other side. And we have here negative I1, 4, which is correct, and then negative I2, and then 6. Okay, this one is just already transposed on the other side. So that's the reason why this one is already positive. Okay, but anyway, so we have these equations right here. And then here is the, simplified version of that one using or with having those values. And then after that, you can now apply two simultaneous equations. Okay, so in here, I did show the solution for the two simultaneous equation. So I did multiply the this equation number 1 to 4, and then this one into by 1. So I didn't do anything. So why did I do that one? For me to be able to eliminate the I sub 3. So after eliminating the I sub 3, then you can now have one unknown only, which is the I sub 2. So after that, you can now find the value of I sub 2, which is 1 ampere or 1 amp. Okay? So after getting the value for I sub 2, you can actually substitute this one, okay, either of those equations. So this is another way for you to be able to get the value of your I sub 3. Okay? With that, you'll be able to get the value of your where is that one of your I sub 3 right here, I sub 3, which is 0.5 ohms. But then here I just I became consistent, wherein I did apply again another simultaneous equation. So I did multiply the first equation by 4 and then the second equation by 10. So with that, you will get the same value for your I sub 2. So that you can now eliminate this one, and then will give you one unknown variable only, which is the I3. And then simplify this one a little bit more, and then you will get the value of I3 as equal to 0.5 amp. Okay, and after that, you can now use the value of I2 and I3 to get the value of I1. So 1 plus 0.5 will give you 1.5 ampere. Okay, so you can verify this one using Ohm's law, of course. Okay, so try to combine this one using parallel law and then get the total current and try to compare if you will get the same value, which is 1.5 amps right here. Okay, so were you guys able to get the concept so far and how to solve the uh, example number 3? Okay, so I didn't ask if you guys were able to get on how did you get those equations. That's because of course we didn't do those anymore. Okay, so I will leave this one as your uh, self study exercises. So that's the reason why I only asked you guys if you guys were able to get the concept. Okay, that's the important thing and how to solve a certain circuit, and you're going to apply Kirchhoff law. Okay, well, anyway, just go here again later on after this discussion. Okay, just read everything again and then try to do that one on your own. So that's why this one is very big. I highly recommend you guys to redo this one using an actual paper. Okay, and if ever that you cannot still not understand anything, so feel free to message me so that I can give you more advice and then I can give you more reference maybe on how to solve using a Kirchhoff's law. Okay, so that's it for this example right here. So this is just another concept. Okay, so we have loop number here. Of course, we only have loop one since this is a one closed loop. Okay, but more explanation when it comes to summation of voltage, just equal that 1 to 0. So I will leave the reading part to you guys. The same with this one. So Vs plus minus I. So this is just basically the voltage or the KVL law. Okay, so with this equation, so it's negative since this is a voltage drop. Okay, and then by transposing those two on the right side, you will get this new equation right here. Okay, and then since they are in series, so we have one value of current only. So you can also do this one right here. Okay, so put the I on the outer side and then multiply that one on R1 plus R2. So after combining those R1 and R2, you will realize that it's actually the R total already. So you can also do this one right here, I times R total, wherein R total is R1 plus R2. Okay, and then in here, you can also do this one using this I is equal to V divided by R. Okay, so V divided by R total, which is R1 plus R2. So if you want to get the individual voltage of R1, so it's VR1 is equal to I times R1. Okay, so initially we only have I, which is the Vs divided by RT, or this Vs divided by R1 plus R2. So we can use that one to replace this I right here. So Vs, which is this one, times R1, which is now this R1 right here, divided by R1 plus R2, which is now the R1 plus R2 right here. Okay, so it's just a matter of manipulating, okay, your equations right here using Ohm's law, okay, etc., etc. And then if you want to get the VR2, then you can also do this one. Okay, so the only one that differs is the numerator. Okay, so let's have an example using this diagram right here. So we have, my bad. This one is 2 resistors only, but this one is 3 resistors. Anyway, so let's do this one using the paint. So we have here voltage source of 12 volts. And then the first one is 10 ohm. Second one is 20 ohm. The third one is 30 ohm. So again, sorry for my ugly handwritten. Anyway, that's the circuit for this one. And then calculate the total resistance, the circuit current, the current through each resistor, the voltage drop across each resistor, and then verify that one using Kirchhoff's law. Okay, So here's the solution explanation. So of course, just by adding everything, 10 plus 20 plus 30, you'll get the R total, which is 60 ohms. And then for the total current, of course, we already have the total voltage and then the total resistance, and you can already use that one. So I is equal to 12 divided by 60 will give you 0.2 amps or 200 milliamp. Okay, so those two are just the same. Okay, so that's it for the A and B. And then for the letter C, so we can already uh, solve for the individual currents just by saying that I total is equal to IR1, IR2, and then IR3. Since they are in series, so you only have one single value for the current. The same with the voltage drop. Since they are in one connection only, so you have the same current, 0 0.2, 0 0.2, 0 0.2. The only one that differs is their individual resistor. So that will determine how much voltage drop it will consume. So for the R1, it will give you a voltage drop of 2 volts. For the I2, it will give you a voltage drop of 4 volts. For the R3, it will give you a voltage drop of 6 volts. Okay. So yeah, that's basically it on how to solve this example number 4. So did you guys get the idea or the concept? Okay, what about the others? So please type also how many percent, just a little, sir, you know, any feedback will do. Okay, as long as you have a feedback, that's already a big deal to me. That only means that you are really listening. Okay, like unlike the others. So I'm not really sure if they are in front of their computers right now listening to me. Anyway, so I'm glad that there are still at least 2 or 3 who are, uh, how do you call that one? Mm, masipag, okay, or dedicated, yeah, still dedicated in learning this topic. Okay. All right. So more solution explanation, etc., etc., or how to verify this one using Kirchhoff's voltage law. Okay. So we just simply did a one loop, of course, the original voltage source, and then 3 voltage drops, and then those given values, and then the result, and then 12 minus 2 minus 4 minus 6 is equal to 0. So if this one is equal to 0, meaning those values of yours are correct, or those process of yours that you did in here are actually correct. Okay, and then here's the labeled diagram. Okay, so the voltage source, uh, the current that is flowing, and then the voltage drop, okay, or the voltage across. So maybe you guys are wondering on what is the difference between voltage drop, voltage versus voltage across. Okay, so well, actually they are just the same. So voltage drop is the voltage that this component accumulated. Okay, the same with the voltage across. So this one is much more straightforward since the voltage across through this resistor is 2 volts, and this one is 4 volts, and then this one is 6 volts. So if you're hearing, let's say, alternating words when it comes to voltage drop and then voltage across, they are just actually the same. Okay, so just to avoid confusion when it comes to those terminologies, drop and then across. Okay, and then here's I think the theory behind blah 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 blah. So just a summary, okay, about Kirchhoff's law. Okay, so here's the reference as usual. My bad. This one didn't came from All About Circuit, but this one now came from all electronics tutorials. Okay, so just visit this one if you want to see the complete version of my examples right here. So yeah, that's it for the module 2. So what we'll do next meeting is, if you guys are willing, okay, if you guys are willing, we can actually have up to part 5, because I'm not really sure if we can finish 3 modules next meeting. But supposedly, we'll be able to finish the module 3 and 4 today, but I don't know what happened. We are too slow right now. So yeah, basically the main concept of Maxwell, 80% of it came from the Kirchhoff's law. So that's the reason why, after learning the Kirchhoff's law, you will be easily understand the Maxwell, as long as you were able to understand the Kirchhoff's law. Okay, so I highly suggest you guys to master first the Kirchhoff's law before jumping in and then start learning about Maxwell. Though I I'm making sure that once you've learned the Kirchhoff's law, everything now is super easy in Maxwell. Why? Because using Maxwell instead of Kirchhoff's is a lot easier. Okay. Well, we'll discuss that one next meeting, so you will know next meeting what are your differences. Okay, but 80 to 90% they are just the same. Okay, same concept. So yeah, that's it for today. So since we are already done with the module 3, then I guess you can now start uh, practicing, especially this one, 2, and 3 for the active jobs. Okay, then if you want, you can also visit these 3 practice exercises and then have an advanced study with the module 4. So that's also okay. That's actually perfect for me, so that once we have the next meeting, you already have an idea how to apply the Maxwell. Okay, and if you want, you can also start answering the Kirchhoff's law quiz. So this is 110 points. So the due date is July 5. So don't you guys worry. You guys have plenty of time. You guys have 1 week, before uh, end up and lose time before you can take this one. So as early as of now, I would like you guys to do a lot of practice, especially in Kirchhoff's law. Okay, because this one is 110 points. So after you're done in analyzing this one, then you can now start analyzing the Maxwell. And you can now also start answering this one if you want. Okay, so it is completely up to you, since this one is already open. However, you will only have one attempt, of course. So having a second attempt is not allowed, of course. So whatever is your score on that first attempt, then that's already it. We cannot do anything about it anymore, since giving you a second attempt is considered as cheating already. Okay, and do not also forget to answer the case study number 2. All right, so just read the facts and then the question, and then just share your opinion with that. Okay, so I guess that's already it for today. So do you guys have a question so far or clarification?
Wala naman po, sir.
Okay,
Wala po.
so sorry. It took us longer than I expected. Anyway, so just continue the module for next meeting. Okay, so if you guys don't have a question anymore, then you guys may now go, and then let's just meet again next meeting. Okay, so goodbye and thank you.
Thank you, sir.
Thank you too.
Thank you, sir.
Thank you
Thank you,
too.
sir. Goodbye po.
Thank you and goodbye too.
Thank you po.
Welcome.